تتعدد التخصصات التقنية.
Your Excellencies, ladies and gentlemen, good morning, everyone. We are honored to have you at the 6th Conference on Mathematical Sciences and Applications, a 3-day scientific event enriched by keynote speakers, participants, and distinguished attendees of professors, students, and interested parties. We are pleased to begin the first session, chaired by Professor Dr. Abir Al-Harbi and featuring Professor Youssef Ouknine, Professor of Mathematics, Al-Qadi Ayyad University, and Muhammad VI Polytechnic University.
Good morning, everyone. I'd like to welcome you to King Saud University. Our visitors. We're really glad to see you today. This is our conference from the Mathematics Department, Science College, and it's also partial with Mathematics Association, Saudi Mathematics Association. So for our first session, we have a program that is full of interesting sessions for the couple of days from now. And I think most of us are going to find something interesting in these talks. Our first talk is going to be Professor Youssef Ouknine. He's from Qadi Ayyad University in Morocco. He's here to talk to us about optimal stopping under modal uncertainty. He's a professor from graduated PhD from Pierre Marie Curie University, and he's a co-founder of the Excellence Center and also of 2024 World Academy Science Fellow. And he's also have done many research in the area of stochastic process, optimal stopping, and financial mathematics. So we welcome him.
I want to thank all the organizers of this interesting conference for this nice invitation. This is the first time in Riyadh, and I am happy to introduce my talk, which is the optimal stopping and model uncertainty in general setting. This is a talk jointly with my co-authors Ihsan Agharas from Linnaeus University from Sweden, and Siham Bouhaddou from Qadi Ayyad University, and Astrid Ilbert from Linnaeus University in Sweden. Okay, what is the origin of this optimal stopping is the following. I will introduce the motivation of this, the first motivation of optimal stopping. Imagine that you have a one position to for a job for one secretary. You have a lot of candidates for this, and the problem is the following. After imagine that you have any candidate for a secretary job, and those candidates are interviewed in a random order with uniform probability, and you want the rule of this study is the following. After each interview, the candidate is accepted or rejected. When is accepted, that I mean, for example, if the KM candidate is accepted, then I reject all the other candidates. If it's not accepted, then is rejected definitely. It means this is the rule of this selection, and the problem is to find the best way to have, which give us a high probability, an algorithm to give us a high probability to select the best candidate for this job. This is the introduction of optimal stopping. The objective is to select the best candidate in this huge of candidate for one position. For this, which is called the 1/u law, or 0.37 law, is the following. This is the rule to select the best candidate. We reject the high probability is 1/8 is around 0.37. It means that in this huge of candidates, you must reject it n/u applicant, and you after that you look for the best one after this benchmark. It means that, for example, if you have 100 candidates, you interview with 37 candidates, and after this 37, you take, this is the algorithm, you take the best one after this. It means that the first 37 candidates over this 100 interviewed with this 100 candidates must be rejected, and after, but we have in mind the best candidate, and after that we are looking for the best. It means that the 37 candidates are only used as a benchmark for selecting the best one. Excuse me. This is called the law 1 over U. For we give a numerical example. Imagine that you have 15 candidates. This algorithm told you that if you for example, if it's small, if you interviewed only 2 candidates, this is too small. It means that maybe you have a great probability that the best one comes after these 2, because you have a small probability that the first one is the best, is very, very small probability. For example, if we have 100, the probability that the first one is the best candidate is 0.01. And this is very, very small. And we are looking for, by this algorithm of 1 over U, 37, this called 37 algorithm, we go from 0.01 to 0.37 probability. For this numerical example, this is not the good idea, because if you select only, if you told that if you take one, the first one or second one is the best, this is very, you have a small candidate, because small probability you have the best one, because maybe you have a lot of candidates who are waiting to be interviewed. Probably the best one comes from some comes from the 2 or some others. Okay, this is also is not good, because if you interview, for example, 11 candidates in this series of candidates, this is not good also, because this, if you arrive to 11, it means that you rejected all the 11 the first candidate, because this is the rule of the algorithm, and this is not good. But the good algorithm is the following. It must be in this candidates, 15 candidates, you interviewed the 6th first, and you notice the best one. For example, the best one is the 3rd. Then after the 6th, you look for the profile which have the profile which is better than the 3rd one, for example. Okay, this is the good idea. This algorithm of 1 over O give us this thing. Okay, this one is not the right one. This is not the right one, but the right algorithm give us this possibility. It means that the steering committee interviewed the 6 candidates, and after that, this is a benchmark. Look for the best one in the rest of the 5. This is the calculation of this n over 2 is some comes from the law of large number in mathematics. So we have to calculate some integrate, and you have this. This is the right one. Is 0.368 approximately. Is this 1 over U. This also another example is the so-called American option in mathematical finance. For example, if you have you have an opportunity, the option to in modern mathematical finance in the market, stochastic market. This one, when you want to price, to have the fair price of American option, who give you the right but not obligation to make some decision at maturity time t with some exercise the strike K, then you have you have to price this. You use the optimal stopping because every day you have the right. We suppose that the market is fluid, and every day you have the right to buy or to sell something in the market. Then for this application of this is the optimal stopping also. Okay. Now let us come to mathematics setting. For this, let us consider a probability space which consists in omega is a non-empty set in the F is sigma algebra with some filtrations. The filtrations Ft represent the information that we have at time t, and some probability P is some measure defined on F, and that has given some reward Yt, which is a collection of in the collection of stopping time. Okay, what we want to do is to maximize the expectation of this reward indexed by stopping time. Is a maximization over all stopping time. It means that we want this is the problem. We want to maximize this expectation. Okay, this is in red. We want to maximize this expectation of our reward. The maximization is down under all optimal stopping with respect to this filtration, and we want to found this maximum, and also the tau star is called optimal if this maximum is achieved in this tau star. It means that the expectation of Y tau star is equal to the supremum of all the expectation of Y tau indexed by all stopping time. And this is called optimal. This is the problem, is an optimization problem in but optimization, functional optimization over all stopping time, which is not not countable, and they have some difficulty to solve this problem because the difficulty comes from the set S is not countable. Then you have the supremum of some on a set which is not countable, and you have this the process, the reward process Y is not regular. It means that is not RCL, L is not Cadillac, also the continue à droite limite à gauche is not a few regularity. There is no regularity of this process, and in general theory of processes we have some difficult to face this irregularity, but you use some optional or predictable processes. Well, the example I told you is the American option. Okay, let us give some continuous rewards. It means that indexed by continuous time. We can do it to see by discrete time like a Markov chain. That YT is adapted. Adapted it means that at time t yt is ft measurable. We don't have anticipation, and progressively measurable process with the first with continuous path, such that this expectation, we need this hypothesis, the expectation of the supremum of the absolute value of reward indexed by time t is less than this, and the main ingredient to solve this problem is the so-called Snell envelope. Snell envelope is Snell is an American mathematician who introduced this process, which is the key of this approach of optimal stopping. R is equal to the supremum of all stopping time to which greater than t, is that stopping time in the future, of the expectation of Y, the conditional expectation of Y tau conditionally to this sigma algebra Ft. This is called RT, is called the Snell envelope. It means this RT is the smallest supermartingales, which is greater almost surely than this reward. And the problem is to determine this small supermartingales, which greater is called Snell, is called envelope of this Y. Okay, this is small supermartingle which bound Y from the above, and with this terminal, achieved it means that at time t at the origin you have the value of RT is equal to YT. This is the K the key of this approach to determine some optimal quantity, we need this Snell envelope. We want to calculate how to calculate this this RT is equal to the supremum, the overall stop and time t, which is greater than t of the conditional expectation of yt, y2 conditional to this sigma algebra ft. To determine this is called Snell envelope, and the optimal stopping, the tau star. You recall this tau star is the infimum, the first time where this Snell envelope hits the reward. The first time that this super martingales, which above our y, hits y. It is the first time, the infimum of time, this is stopping time, because the hitting time of some optional sets. Tau star is equal to infimum of t, such that RT, this Snell envelope, with super martingale, small super martingale, which bound y above, hits this y. This is optimal. This is called the smallest optimal stopping, because we can find very this is the small stopping time. There is no uniqueness, because this tau star, okay, this tau star is not unique, because we can find tau star or another stopping time such that this they achieve the maximum of this expectation. Okay, this is some picture of some derivatives, some in the market. When you have this is the maybe the blue one is the blue one is Snell envelope, this RT, and the red one is the reward YT, and this tau star is the first time that these two curves collapse. This one is tau star, and the tau max, tau star max, is the first time with these two curves becomes different. This is by the Doob-Meyer decomposition. In this are all the stopping time which are in between tau star and tau star max are optimal. It means that the real is the optimality. It means that the supremum of y tau is equal to y tau star for every yt for every t between tau star and tau star max. This is the good. This is, for example, in mathematical finance, this is the good area to optimize the expectation. For this, I give an historical result about this fact. But in the case of right continuous with limited processes, it means that our reward y has some regularity. It's not continuous, but they have. This is solved by Sharayev and Del Karoui, and the value is the RV. We want to determine RV, which is a process which is equal to the essential supremum of this stopping time, which is greater than V of the conditional expectation of y tau with respect to FV. This is the Snell envelope. The difficulty is to compute explicitly this Snell envelope. But this, as you can see, this is only a family of random variables. This is not a process. There is no process here, because RV is not is not the value of a process at time v, but only a family, like pictures of random variables indexed by stopping time. And we will make, the problem is to transform this family of random variables indexed by stopping time to a process taken indexed by stopping time, the so-called aggregation. Okay, we must to make an aggregation such that to glue all the family RV, because this is a family of random variables. There is no process for the moment. There is no process. And the problem is to look for some process like this, that R indexed by V is equal to this random variable RV. Two things very different, almost surely. This is this RT, this is new process, is called Snell envelope. It's small super martingales which bound our reward y. This is the objective of my talk. And the first one who gave this is the thesis of Mengele, which published in a Seminar of the Probability. And the construct for the first time, when y is optional, this Snell envelope by approximation by some with the help of some result by Jean-Michel Bismuth, the first one who solved this problem for some reward process. And we found this optimal optimal stopping is the first time such that the Snell envelope hits the reward yt. And this is very important. This is we need to know this RTI. This is very important. This is and also by Kobylinski and other El Karoui and all other people. In Andrewick assumption, like the semi-continuity of we have some hypotheses like the semi-continuity, which is very important to have to glue this family of random variables on only one single process called Snell envelope. We need this property, the limit sup of the expectation of y to n, when to n is stopping time which goes to tau is less or equal to this expectation. And the optimal stopping is this one. For this, I will give you the result for when we have, this is only when we have one probability, okay? This is only when we have one probability, I in red. But for this, we need, in the case when we don't have this right continuous with this limited property of our reward, we can also work with some so-called family of Snell envelope, and we don't make aggregation. But for this is not Snell envelope, but only we can stay in. This is done by Kobylinski, Kines in their famous paper. For what is interesting for us is to change. We are all of these papers are done with single probability, when we have only one reference probability P. But I will do this, I will extend this to several family of no countable family of probability. This is the called uncertain. We are in the uncertain world. It means that we don't have only a probability P, but we have a set of no countable probability. Okay, this is this is called the uncertainty, and we want to do the same work, the same to have the good strategy, the good optimal stopping to maximize some expectation, but some family of expectation. But no, this family of expectations comes from no countable probability. Okay, for this. We give some family P script is the family of probability which are equivalent to someone Q, which the family is family of probability P which are equivalent to one probability Q. This is at the beginning only you have this P script is single value, but for this one we have a lot of family of probability. It is that the model is called uncertain. We are not sure about this model, so we have many scenarios. And for this, we want to make optimization with respect to stopping time and with respect to many probability family of probability measure, which are equivalent to some given one. And then you have optimization with respect to a couple of optimal stopping and probability also. This is our problem, is to look for a pair of one probability P star and one stopping time tau star, which belong to set of this probability cross the set of stopping time, such that this we will call it strong Snell envelope such that this is shaved. It means that this R is equal to the expectation with this new, with respect to this new probability P star of at Y indexed by this time to star. It means that we have a couple, we have a maximization. For this, we define the so-called generalized Snell envelope, which is defined on our paper, which appear in soon, maybe 1 month or something like this. We are looking for this this RV, this family of random variables, which is the essential supremum, because essential supremum, because we don't take supremum, but essential supremum to conserve the measurability property, because we have a set of P which is not countable. The set of stopping time also is not countable, and to have some measurability, we must to take the essential supremum of the conditional expectation of Y tau. This family Y tau is family of random variables, conditional to the FV, the sigma algebra FB, but this taken with respect to probability P, and you have the maximization also with respect to this probability P and tau. So we have double maximization. We have the so-called Snell generalized Snell envelope. And the problem is to, for this, this is important for aggregation, because at the beginning, we have only a family of random variables like Y tau and Y tau prime. They are compatible, or they are, if we have this property, this very important property, for this, the second one, the first one is some measurability with respect to Y tau is F tau measurable non-negative random variable. And for two stopping time tau and tau prime, we have this equality. Y tau is equal Y tau prime arbitrarily on the set tau is equal to tau prime. This is very important. If this property, and you have some regularity, some like upper semi-continuous in expectation, then this family of random variables Y tau can be aggregated to one process. It means that we have some stochastic interpolation. It means that there is some true process Y or X such that Y for every tau stopping time, Y tau is equal to the value of this process at time tau. It means the interpolation. Okay, we have this is called Snell envelope. Okay, this is the remark. This process, this is a difference between Y tau and this is Y tau is a family of random variables, and Y tau is the value of the process at tau at time tau. We are looking for this. The right one in the right side. We are looking for the Y in the right side, and this is we will make some aggregation. Okay, but for this we need some regularity to define. This is a family of which is in red is a family of random variables indexed by stopping time, which will be aggregated to some process, and this process is the K of our approach. It's the general Snell envelope, and they give us the optimal stopping. For this, we need some regularity on the densities of our family of probability, because the P script is the family of P, which is equivalent to some probability Q. Then you have by radon-Nikodym property, we have some densities, and these densities maybe we suppose that they are L0 convex. It means that width is a convex when is multiplied by the convexity is 1 minus alpha combination of two things belongs, but this alpha now is random. You call it the L0 convex. It means that when we have a combination, convex combination by some L0 random variables, then it lies also on the set Z. This is a technical hypothesis on the radon-Nikodym densities of our family of densities. Okay, excuse me. We have some Bayes rules. We have some to calculate the link between the conditional expectation with respect to P in the conditional expectation with respect to Q. This is the well-known called the Bayes rule, Bayes formula, and we have this important fact. We have some admissibility for V plus and V plus. It means that when V is equal to V prime, then RV is equal to RV prime. These two conditions to admissibility, because these two conditions is necessary to they are sufficient to glue all this family of random variables on one process, and this process is called the Snell envelope. Okay, this some optimization because we need to pass to the approximate by some sequence. Okay, and we have this. For this, we define the P super martingale family. P because we have a lot of a set non countable of probability measure which are equivalent to 1Q. So we call this super martingale. This is known for when P is single, is only one probability. This is the conditional expectation with respect to P is less than Y top prime. This is martingale. But this, look at for definition, we have this for every P which belongs to this P script. Because this property, this is called P super martingale family. It means that it's like a super martingale for every measure in this set of probability. Now we construct the Snell envelope of this process. There are P super martingale family in sons, okay, and there are this family RV and R plus V is the right limit. They are admissible, okay? Then can be aggregated by a result of Delachery-Langlar about they have a seminal work on the study of aggregation of processes at the beginning of 80s. There are some conditions to glue this family of random variables to one single process, okay? For this, we have the important result. Let us P star belongs to the family of probability P into star belongs to the family of stopping time, such that this X in Y is positive. This family of random variables are positive, such that the expectation is finite. The stopping time in the to star in the probability P star are optimal in this sense. It means that the supremum of P in the supremum of stopping time T tau of this expectation is achieved in this P star and to star. It means that we have the optimization with respect to things, with respect to family of probability, and we have some property for their density and stopping time. Okay, and we have the criteria to. This is the criteria to be optimal. It means that they are optimal if and only if the value at optimal stopping the process and the reward in this R, which will be called the general Snell envelope coincide. And this property, it's not only a super martingale, but when it is stopped at this optimal stopping, becomes a martingale family. Okay. It means that we have, instead of we have less or equal, we have equality. This is the criteria 1 and 2, if and only if are satisfied, if and only if we have this 12. It means that this is the criteria to be satisfied if we want to have some optimization with respect to things, with respect to probability family, and optimal in the stopping time families. Okay. Okay. For this, we need some approximation, what we call, because optimal stopping is otherwise difficult. So we have 1 minus alpha. We perturb by this by minus alpha optimal stopping, and for this we have the result. This is only for, I don't have aggregation for the moment. We have only family of random variables, and we call this family of variables are optimal in the sense that they achieve this, because here you have only a family. Why? Only a family, in this RP is also a family. So we want to glue this two family of process on one process called Snell envelope, and this is the optimal models. And after that, we make an aggregation at the end to have the good process. Okay, from this we introduce so-called Doob-Meyer-Mertens decomposition to have to characterize the optimal stopping. Okay, donc for general payoff, donc we have this an admissible family. Let us give an admissible family of random variable. If it's not necessarily negative, then we can make some hypothesis. If we have only this negative part of the supremum is finite, then we can drop the positivity of the reward, and we have the same result. RV is essential supremum of P in the essential supremum of tau, which is greater than the stopping time V of this conditional expectation, and they give us the optimal things. Okay, and for this, to characterize the maximal stopping, because I told you this tau star and tau star max, we need some the so-called Doob-Meyer-Mertens decomposition, is like, which is known, very known, is Doob-Meyer decomposition. He told you that every super martingale can be written like a martingale plus some predictable increasing process, but here a Cartlack process. But for Mersenne, you have three process, means that you have every P super martingale can be written like a martingale plus some increasing process, which is Cartlack, plus some pure jump process, which is predictable. And for this three process, we construct the optimal stopping, maximum optimal stopping. Okay, thank you very much.
Thank you, Professor, for this interesting talk. Are there any questions from the floor? في أي أسئلة؟ في أي سؤال؟ So I think, thank you, Professor, for this talk. And if anyone else have any questions, I think we can receive it by email. Oh, there's one over there.
Thank you for the talk. During the talk, you refer to essential supremum over a set of measures. So I'm assuming we have a measure over the set of measures. I just would like to ask, what kind of measure is that?
Okay. Thank you very much for your question. Because if you have a family of measurable function, these are f tau. This is a family of measurable function. That is when the family of indexation is not countable, the supremum is not measurable. The family of the supremum of measurable function is not always measurable. So we need so-called essential supremum, which have the same role as the supremum, almost is equal to the supremum almost everywhere, but the essential supremum is measurable. So we can make integration, because we need regularity, because we need the integration in stochastic calculus with this essential supremum. But with the supremum, it's not necessarily measurable. So we can't do anything for the supremum, because the set of my indexation, the set of probability P script, or the set of stopping time are not countable. If is it countable, okay, the supremum of Fn, for example, when Fn is measurable, the supremum over n is measurable also. There is no problem, because you have a limit of sequence. But when the indexation for example, y tau or some indexed by t or by tau, the supremum is not measurable. It is not always measurable. So we need some. This essential supremum is introduced by Dulachery, and they play the same role as the supremum almost everywhere. This is okay. We use this essential supremum. Okay. This is for technical reason. For technical reason of measurability and to do some good calculations, we use this essential supremum instead of supremum. Thank you very much for your question.
Thank you. Another question? Okay, thank you.
Thank you very much.
Professor.
شكرا بروفيسور يوسف وبروفيسور عبير. ننتقل الآن للجلسة الثانية برئاسة الأستاذ الدكتور محمد القويز، ويتحدث فيها مشكورا البروفيسور كريستيان بومر من جامعة كلية لندن.
Thank you, Professor Youssef and Professor Abir. We now move to the second session chaired by Professor Dr. Mohammed Al-Guez, in which Professor Christian Boehmer from University College London will speak.
Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone to the session of the conference on mathematical sciences and their applications, sponsored and organized by the Saudi Association for Mathematical Sciences at King Saud University. Our speaker this morning is Professor Christian Boehmer, who is a professor in the Department of Mathematics at the University College London and an honorary professor at the University of KwaZulu in Durban, South Africa. He is also head of the Department of Mathematics at the University College London. Professor Boehmer's research interests are in theoretical physics and applied mathematics, and more specifically in the mathematical foundations of general relativity and dynamical systems applications in cosmology. And his talk today will be on the subject of dynamical systems in cosmology. Professor Boehmer.
Thank you very much for the kind introduction, and thank you very much for the organizers to invite me to speak today. So today's talk is on dynamical systems in cosmology. So what I'll do is I'll give you a quick introduction of what these equations are. Then I'll give you a crash course on cosmology, and then I'll put this all together for the rest of the talk. So if you are the kind of person that thought, oh, I really want to see some equations in cosmology, and you never got around to do this, so in this talk you get a very quick introduction to this. And I have quite a bit of material, so if I start running out of time, I shall eventually just skip to the end. 1 second, I'll set myself a timer. Right, so I tell you what dynamical systems are, or systems of ordinary differential equations. I'll tell you about cosmology. Then I tell you about some advanced methods that we're using. And towards the end of the talk, I will actually give you some open mathematical questions that I don't know the answer to. So if any of you knows how to do this, then there's some scope for work. So firstly, what's an ODE? So all of you will know what an ODE is. You have some, the derivative of a function on one side, and then an function on the other side that depends on the function itself and possibly a coordinate like time. And what you want to find here is the unknown function y of t. And under certain regularity conditions, you can actually prove that the solution always exists for a small amount of time. This can easily be extended to n equations. So you simply have one equation per function, and you have n right-hand sides. And again, under certain regularity conditions, you can always show that solutions of these equations exist at least for a small period of time. And all the equations I'm looking at, they have one specific property, namely that the right-hand side of my equations do not explicitly depend on time. And under these conditions, one calls these equations autonomous. So any system of ODEs that doesn't depend on time explicitly is called autonomous. And once you have an autonomous system of equations, which we usually, click too quickly, we usually write this in a vector notation. So the boldface letters here are simply the collections of the previous functions. And whenever you have an equation of this type, where you have a left-hand side which depends only on first derivatives, and the right-hand side that only depends on the functions without the explicit time dependence, you always call this a dynamical system. And you might briefly think, hang on a minute, that is quite restrictive. But I will show you in a moment that actually this is a very broad class of equations that you can study. So this is, in a nutshell, the existence and uniqueness theorem, which tells you that solutions to these equations are meaningful and exist generally for a small period of time. So between minus a and a, provided your functions on the right-hand side are at least C1. But I'm only mentioning this very briefly, not going into the details. This is sort of well-known material. I'm giving you one very quick example because I said some of you might say, well, many equations in nature are second-order equations or maybe even higher order. So why are dynamical systems useful? Well, if you just take Newton's equation and assume it's autonomous, you can, instead of using the acceleration, you can introduce momentum, and you can simply rewrite Newton's equation into a pair of first-order equations. So basically, if you give me any equation of any order, provided it's autonomous, you can always force it into the form of a dynamical system. So which means dynamical systems are kind of broad. So they're not restricted to first-order systems. You can use any order systems, but you can always rewrite them in an appropriate form. So again, provided F does not depend on time explicitly, this is again a dynamical system. And you can apply the same trick to all kinds of equations. And this is a number of equations which are all of the form of dynamical systems and where they appear. So you all remember a few years ago we had this pandemic that changed our lives massively. You can easily model COVID-19 using the so-called SRI model and some variations thereof. There's models which are called Lotka-Volterra models that have been known for many years, which are also of the same form. And then you have population dynamics models. Some of you might know the Lorentz system, which displays chaotic behavior. Or at the very end, cosmological dynamical systems. So these are the ones I'm interested in. So there's a huge array of literature that exists on the general topic. And once you're dealing with a system of autonomous equations, you have a certain amount of technology that you can exploit. And that technology is well developed in the applied maths literature. So the standard topics are phase space analysis, fixed or critical points, and linear stability. So this is the stuff that one normally does. And then there's a huge catalog of advanced models or advanced techniques. So Lyapunov stability, center manifold theory, or KCC theory, which I'll mention very briefly. You can also study points at infinity. So exists an entire suite of techniques that one can use. Yes, okay. So if we have a dynamical system of this form that I've prescribed, the most important definition is that of a fixed point. And a fixed point is simply a point where the right-hand side vanishes. So and if you imagine this, if you have a system of this type where all your derivatives vanish, that means that you are locally at a point where the system is at rest. And the natural question you would then ask is, well, what can you say about stability at this point? So many of you have water bottles. If you take a water bottle and put it upside down on its lid, give it a little nudge, you will see it will fall over. But if you have the bottle the correct way around and give it a little nudge, it won't move. Or it will move a little bit, but it will come back to a point. So you can sort of easily, with the water bottle, distinguish a stable and an unstable point. And so this is a very natural question to ask for these dynamical systems. And to understand this and how this works is actually quite straightforward. So you assume there exists a point where the right-hand side vanishes, and then you simply do a Taylor series expansion on the right-hand side. And remember, we assumed the function is actually C1, so you can do this at least once. And often these systems are more regular than this. But the whole point is that the leading order contribution on the right-hand side near the fixed point is simply the matrix of first derivatives of the function, and this is often called the stability matrix in this case. And linear stability theory is quite straightforward. You simply look at the eigenvalues of the stability matrix, and that tells you how the solution behaves near this point. So this is what I'm summarizing here. So if you're very close to this fixed point, the right-hand side is approximately the matrix of first derivatives evaluated at the fixed point. And you simply determine the eigenvalues, and the eigenvalues tell you whether you are approaching the fixed point or whether you're driven away from the fixed point. This is all summarized here. I should say that if at least one of the eigenvalues is 0, you can't really use linear stability theory. And in this case, you have to use an advanced technique, for instance, center manifold theory, which will determine whether the solution is stable or unstable near this point. And if you have a collection of eigenvalues with alternating signs, you would basically speak about a saddle point. So you have some direction which attract the trajectories and others that repel them. Okay, great. So couple small remarks. So in 2D and 3D, so for systems that only have 2 or 3 equations, you can actually fully classify all these fixed points. And in higher dimensions, you can't do this. And it is perfectly fine for your eigenvalues to have complex conjugate eigenvalues, because they make perfect sense in this kind of setting. And this has to do with the fact, so if you think about a solution to your equation being e to the lambda x or e to the lambda t, if lambda is a complex number, then that's fine, because you just get then trigonometric functions out of this. And then the third point here is, so if you have a 0 eigenvalue and linear stability theory cannot be applied, you can nonetheless deduce that the point is unstable provided at least one other eigenvalue is positive. And this simply comes from the fact that the direction related to this eigenvalue is always a repeller. So you only really need center manifold theory when your eigenvalue is 0 and all other ones are negative. And then you really can't say anything with linear stability theory. So this is a very quick reminder of systems of ODEs. And now I'm jumping straight into a crash course to cosmology. Are we with time? Yeah, time is going well. Okay, so quick crash course on cosmology, which you probably have not seen before. I will show you 2 pictures. So if you talk to people who do cosmology, they can tell you that the universe is roughly 13.6 billion years old. And they claim that they can look back almost 13 billion years and tell you roughly what happened, which is quite a miracle. But you sort of, I believe them, it looks all pretty good. On this graph, I want you only to look really at the red line. So the red line seems to be approximately the expansion history of the universe, starting from a Big Bang, which is a very large explosion that we don't really understand. But if you go back in time and observe the universe, you see that at some point it underwent a period of very rapid expansion, which we call the Big Bang. And then the universe just evolved roughly to its present time. And if you look forward, it appears that it will follow most likely the red trajectory and will keep expanding faster and faster. Second picture I'm showing you is roughly more or less the same thing, but there's a little object on the right which is called WMAP. It's a satellite, and that has been collecting data for a long time now. And basically what the satellite is doing, so you see you have this little turquoise region on the left. So the satellite is looking, that is emitted from this little turquoise region. So if you imagine that your universe started with a very massive explosion and was very dense and hot, so at very early times, light can't really propagate freely in this kind of early universe that just exploded and just started to exist. But at some point, as it thins out, at some point light can freely propagate. And this last surface where the light can freely propagate is what the satellite is looking at. And this sort of informs a lot of cosmological models. Right, let me link this to dynamical systems now. So if you look at the Einstein field equations, in general, they're very difficult to deal with. So the Einstein field equations are, in general, there are 10 equations, they're partial differential equations, and they're highly nonlinear. So in general, it's very hard to deal with them. However, when you do cosmology, things actually become extremely simple because the universe looks extremely symmetrical. So on very large scales, the universe roughly looks the same in every direction, and it roughly looks the same everywhere, which means, more mathematically speaking, the Einstein field equations that you're studying, you're actually only interested in the Einstein field equations. They're homogeneous and isotropic. And if you combine these two statements, homogeneity and isotropy, with the Einstein field equation, it actually boils down to ordinary differential equations, which is what the first part of the talk was about. So basically, when you do cosmology, you're actually studying ODEs. And once you're studying ODEs, and in particular a system of ODEs, then it makes sense to study dynamical systems. And then this whole thing starts to come together very nicely. So there's 4 people usually credited for the way we now describe mathematically modern cosmology. So these are Friedman, Lemaitre, Robertson, and Walker. And this is all work that was done in the 1920s. And the Einstein field equations, assuming that you apply them to the universe, are given here. So you have one algebraic relation, and then you have 3 equations that all contain a time derivative. So the dot here is the time derivative. And the quantities are, so rho r is the density for radiation, rho m is the density of matter, and h is a function of time called the Hubble function. And lambda is a constant, it's called the cosmological. I'll comment on this in a moment. So you see here that you have actually a system of ordinary differential equations. And if you do a simple counting argument, so given that you have 3 equations with time derivatives, and then you have 1 equation which is algebraic, so the very first equation you see has no time derivatives, then a simple counting argument tells you, well, in reality, you're really only dealing with 2 dynamical equations. And what I'll do now is I'll rewrite those equations slightly, and then you will see that they actually take a much nicer form. So the idea behind this is you introduce 3 new functions, and what you do is you take this algebraic equation and you divide by 3h squared. And if you divide by 3h squared, you see the first term becomes 1. And that looks completely harmless, but if you divide by 3h squared and the first term is 1, it tells you that all the other terms that you've just created are all dimensionless by construction, because you have a 1 there. So everything else is dimensionless, which means all these omegas, which means kappa rho m over 3h squared, and all the other ones, they're all dimensionless. So this is very nice. And these guys all of a sudden have a natural interpretation. So the first equation more or less reads 1 equals omega m plus omega r plus omega lambda. So you can think about this as saying 100% of the content of the universe is divided into some matter, some radiation, and something that is called capital lambda. So, and in these variables, you can rewrite your equations and they become particularly neat. Namely, they take this very nice form here. And those of you that know dynamical systems, you will spot probably immediately that these equations look somewhat familiar. And the reason why they look familiar is not only are they a dynamical system, they're actually a Lotka-Volterra system. So this is quite surprising that this happens. So these Lotka-Volterra systems, they're usually used when people study predator-prey models. So you have some kind of a situation where you have a fixed piece of land and you have, say, rabbits on there and foxes. And you can study how their populations vary over time. And the cosmological equations, they sort of fit into this general category of Lotka-Volterra systems. And because these equations are so simple, I can do the complete linear analysis in one slide. How does this work? Well, you have to find the fixed points. The fixed points are very easy when omega m and omega r are 0. Both equations are 0. And then if you want the first equation 0, you set omega m to 0, substitute it in the second equation, and then you get omega r has to be 1. And likewise the other way around. If omega r is 1, you plug it into the left equation, and then omega m has to be 1. So your three fixed points are simply the origin and then 0, 1, and 1, 0. And it is because this system is so simple, you can basically do the eigenvalues by hand on a little envelope almost. You can work out what the eigenvalues are of the stability matrix. And you can then visualize the system using a little phase space plot. There it is. So what you get. So there is a reason why the phase space is confined to a triangle, but I don't want to go into this. The main point is here that what you see is that the system is actually incredibly simple. You can solve it completely. And what the linear stability analysis tells you is that, well, everything needs to start at this point R. You have a saddle point at M. So depending on your initial conditions, you can approach this point M and can get reasonably close if you wish to do so. And then eventually you get taken to the origin. And it turns out that this kind of setting, which is implied by the structure of the equation, is actually in agreement with the universe that is observed. So which is kind of nice. So we know from experimental or from observations, from colleagues, I don't do any observations, I don't have a clue what they do. But if you trust my cosmology colleagues that do this, then the universe started or underwent some period that was radiation dominated, it approached a matter-dominated universe, and then goes to this point O. So this point O, which is the origin, if I go back one slide, so if you have that omega and omega r are 0, and you plug this into the first equation, you see that omega lambda is then 1, which means the origin is the point where omega lambda dominates, and omega lambda, well, is the red line. So the red line corresponds to omega lambda dominating. And actually the dynamical systems analysis says that this is what should really happen. So this is very nice how the mathematics of the equations actually are in perfect agreement with all the physical observations. So now, yeah, so I told you all of this. So this is exactly what is happening in this cosmological setting. And now I'm jumping very quickly to, just checking the time. And now I'm jumping very quickly into two other techniques that can be used to study dynamical systems. And then I swing back to some cosmology. You see, so I'm swinging a bit between the maths and the applications to some cosmology. So instead of linear stability theory, one can use a different technology, which is actually kind of nice, to study the stability of fixed points, and this is called the Lyapunov stability method. And in a sense, it sounds really simple, but there's a sort of caveat to it. If you can find a function with the right properties, then you can say something about the stability of a point. The beauty is that you can apply it directly to the equations, and you don't have to go through some other process. The problem is finding that function. So provided you can find a function that is differentiable near this fixed point is positive, and so the final condition is the tricky one. So the function needs to be, so v dot less than 0, condition 3. So v dot here is again the derivative with respect to time, but for my dynamical system, that means the derivative along the flow of the system. So that means if you want to find a v that is a function of your dynamical variables, you need to use the chain rule. If you, I mean, depending on how many variables you have to repeatedly use the chain rule in order to extract what this derivative is, and then the derivatives of the dynamical variables are related to your dynamical system. So the last line here tells you what you do is to find the derivative of v, you need all the partial derivatives of v with respect to its variables, and then you substitute in your dynamical system, so which is why the f's are on the right-hand side. So it is this very last condition that makes it tricky to find such functions. And to the best of my knowledge, there's no general, so if I give you a system of equations, there's no constructive method known that always generates a Lyapunov function. So you need to sort of do a bit of guesswork to find these guys. It turns out for some of the cosmological systems I'm studying, it's not too difficult to find them. And I want to show you one little result of why this is kind of neat. So the point is that, so I'm just stating this Lyapunov stability theorem here. The point is, if you can find a function that has the properties that I've described, the most important one is that the derivative along the flow is negative, then the point around which you found the function is stable or asymptotically stable or globally asymptotically stable. It's not so important to distinguish the three if you're only interested in the statement about stability. And I want to show you one quick example why this is actually kind of a neat kind of technique at times. So this system has a fixed point at the origin, and the eigenvalues are -1 and 0. And I told you that under using usual technology, you can't say anything about the stability. So you would have to use, strictly speaking, center manifold theory to determine uniquely whether this point is unstable or not. It turns out a simple Lyapunov function like this one, so 2x squared plus 2y plus y squared, actually works. So you differentiate this, you substitute the equations back in via the chain rule, and you see that this function is immediately strictly negative. You don't really have to think about it, it's strictly negative, and therefore the point is globally asymptotically stable. So sometimes the Lyapunov function approach is actually very useful to consider when you are faced with a system where sometimes other systems don't necessarily work. It's not always so easy to find a function, although it's not too difficult either. The last method I want to very briefly mention is called KCC theory, goes back to Kozami, Kartan, and Chan. And the basic idea is to think about equations slightly differently, and it can then be applied to dynamical systems. So if you think about so for instance, Newton's equation and the geodesic equation in differential geometry that tells you what are the shortest distances between points. And you also think about the Euler-Lagrange equations, which are also in general, I mean, they're often second order differential equations. The question you can ask yourself is, well, the geodesic equation is really nice because if you know the geometry of your space, you know what happens with two nearby geodesics. So if the space is positively curved, you know that two nearby geodesics will be attracted to each other. If it's negatively curved, they will move away from each other. So the question is, if I give you some equations, can you interpret them as geodesic equations? And if you could do this, then it would be extremely nice, because then you could always make a geometrical statement about the behavior of the solutions. Unfortunately, it isn't as easy as one might hope. So the question is, can you put any, say, Euler-Lagrange equation into a geodesic equation and reinterpret things? And the answer is no. So if you wanted to do standard Riemannian geometry, you cannot fit in second order differential equations, for instance, and interpret them as geodesic equations. There's basically a bit missing. And that has mainly to do with the way Riemannian geometry is set up. However, it turns out that if you move to a Finsler geometry, then you can do things differently, and then you can all of a sudden, I hope this is coming up. Ah, there it is. So if you move to a Finsler geometry, which is slightly more general, then you can actually fit any second order system of equations into this geometrical framework. And then you can go through a similar process like you would do with the geodesic equation. You would determine the underlying curvature of the space you're dealing with. And the curvature would tell you whether nearby trajectories are attracted or repelled. The process looks slightly different to what it does in Riemannian geometry, but in a nutshell, you need to write your equations in this form, and the very last equation is the important one. So you have some form of a deviation equation that depends on a type of curvature tensor, say, which I call P. And you will see in a moment that this has a very close link to linear stability theory. So I'll tell you in a moment what this is. In the next slide, I'll show you how to compute this guy P. So the moment you write your equations like this, you have some functions G, and these, through a slightly convoluted process, define this object P. So you see it is slightly annoying to write this thing down, and it reminds you a little bit of a type of curvature tensor, but it isn't too bad. In effect, if you think about this from a practical point of view, I mean, it's a simple calculation. It's just slightly an annoying calculation, but definitely not too difficult to do. So in a nutshell, things are actually very easy. So if you think about linear stability theory, what you do in linear stability theory, you take your system of equations, you expand the right-hand side, you extract the linear term, you evaluate it at the fixed point, and that stability matrix, you compute its eigenvalues, and then the signs of the eigenvalues effectively determine the stability of the system near the point. And it turns out that you can use precisely the same technology, provided you have this tensor A, it's tensor P, which is rank 2. You can think about it as a matrix, but it is a tensor. But it's a rank 2 object, which matters the most in this case. So once you have found this guy, you can follow exactly the same process. You evaluate it near the fixed points. You compute its eigenvalues. And again, the signs of the eigenvalues will again tell you whether you should consider this system stable or unstable. And now I'm going back to a cosmological model and show you how all these things play out in this case. And the most interesting thing is that you will see that I have given you 3 different types of stability. So I've mentioned linear stability, which is sort of a standard tool. I have mentioned Lyapunov stability, which always relies on you being able to find a function, and then this geometrical KCC type approach, which at the end of the day, other than that the calculation is slightly annoying, is somewhat similar to the linear stability theory in the sense that you extract eigenvalues from an object, which is, however, geometrically motivated. So the equations I want to study are the following. So I have this system of equations, and this system of equations is sort of typical for the kind of type of dynamical system one finds in cosmology. So usually the systems from a math. So if you open a mathematics textbook on dynamical systems, you will notice a few things that when you work with dynamical systems in cosmology, you find sort of frustrating. So firstly, in any applied, the critical point is always at the origin. So if you look at this system, for example, it has in general 5 critical points, and there's one at the origin, but usually your critical points tend to be everywhere, and you have a multitude of them, and generally they depend also on a parameter. So in these equations here, there's a single parameter lambda, which is assumed to be positive. And you also have that your variables u and v are, oh, there's a y there, apologies, that needs to be a v. So your variables are also constrained to be in a circle. And in fact, so the second condition, y positive, should be v positive as a typo. So actually the physical phase space that we are interested in is actually just a semicircle, or the inside of a semicircle, with the boundary included, to be fair. And you will see immediately that if you look at point B here, which is located at lambda over root 6 and then square root 1 over lambda root 6. So you see there are certain existence conditions for this point B. So for instance, lambda squared needs to be less than 6, otherwise the point doesn't exist. So you always, for these cosmological dynamical systems, you always end up with systems which are, in a sense, a little bit complicated, because always the number of critical points tends to depend on a parameter, and your stability properties will also depend on a parameter. You see point C, which has the 1 over lambda term. So it's x and y are the same, but it's root 3 over 2, 1 over lambda. So there's also an existence condition here, because if your lambda is too small, then this point will be outside the unit circle. So its distance from the origin will be too large. So there will be various conditions like this that one usually has to deal with. Right. So what one finds is is that correct? Yes, that's correct. So before I show the analysis, I just want to show you the typical phase space pictures that one finds. And so the parameter values are lambda, root 2, root 5, and root 8. So root 2 is the top figure, root 5 is the left figure, and root 8 is the right figure. And what you see is that you see the number of critical points changes. So in picture 1 on the top, so point C doesn't exist yet. And what is actually happening here geometrically, so point C comes along the diagonal, and if your lambda is too small, it's sort of outside the phase space. And if you increase lambda, C moves in till eventually it's inside the physical phase space and then moves towards the origin. Point B, as you increase the parameter value, actually moves down along the perimeter of your semicircle till it eventually merges with A plus and then disappears. So there's some interesting things happening with the dynamics of the points itself, but we don't study those. We're just interested in these kinds of questions of stability of these points. So in both pictures, you would assume sort of naturally saying, okay, point C looks stable, and B, well, in picture 1, it's definitely stable, and in point B is probably a saddle. So how does this compare with all the other stability notions that I've introduced? It's actually kind of interesting. So if you go through the linear stability theory, the KCC theory, and the Lyapunov stability, you come up with this little table and those parameter ranges here. And what you find is that there's actually only one point and a certain parameter range where all these different notions of stability actually agree, which is kind of strange. Because if you look at the picture and I told you point B was stable, you would say, yeah, that's fine, I believe this. But if you look at this, you would say, okay, that's really strange. So why does this geometrically motivated theory tell you that these points are not stable? We don't know the answer to that, by the way. It's just what comes out of the analysis. And somehow it's not so clear why KCC theory is so restrictive on stability. But it's quite nice to note that you have 3 well-defined methods to define stability, and actually often they don't agree. And sometimes they do agree, or rarely do they agree. And the noticeable thing is that KCC certainly is the most restrictive of them. And sort of for the last 5 minutes, I want to actually jump into a different system, which is very similar to this system, but has an extra term. And I will finish then with some open mathematical questions, which hopefully you will find a bit interesting. So the next system I'm looking at is a 3-dimensional system. And if you look at the first line of x prime, and you look there, it starts with -3, and then you have, forget the term, the last term with the gamma. So if you just look at the x prime equation without gamma and the y prime equation, you will see, but there's now a third equation for a z variable, and there's this term with the gamma. So the physical phase space is, in the xy coordinate is again a semicircle, but the z coordinate now goes from 0 to 1. So you're dealing here with actually a half cylinder of height 1. And your gamma here is any real number. So it's a second parameter in the system, and the lambda is the same as the previous lambda, which is also assumed to be positive. Now, if you look at the system, especially now looking at this new term with the gamma, you see that you have an x in the denominator and a 1 minus z, which means if you wanted to say something about uniqueness and existence of solutions near z equals 1 or near x equals 0, strictly speaking, all the standard theory breaks down, because the function on the right-hand side there is not c1 at z equals 1, for example. Now, the question is, does it make sense to study points near z equals 1? And this is a good question. So I'll show you the phase space that you find when you numerically solve these equations. So z goes from 0 to 1. So the top is z equals 1, where this gamma term diverges. Now, if you look at the bottom of the phase space, so imagine you look at the bottom of the cylinder where the point D is and the curly bit, this looks very similar. I hope. So what I wanted to show you was that the bottom of this phase space looks actually very similar to the previous 3 pictures I've showed you. But you know, I have this extra dimension, which makes sense because the systems are closely related. So the most interesting point from a mathematical point of view is point E. And that is because point E, strictly speaking, is located on the z equals 1 plane, where this gamma term diverges. Now, these points A, B, D are just your regular fixed points, the ones that you normally deal with. And I like to refer to this point E, a singular fixed point, because it behaves like a fixed point of the dynamical system. However, the equations, strictly speaking, are not defined there. But it looks like the late time attractor. And now I want to show you a little trick that we've developed, which allows us to say something about this point. And then I'll finish. So it looks like an attractor. How can you say something like this? Well, let's do the following. Let's evaluate the stability matrix, taking the limit when z goes to 1. It turns out that the first 2 eigenvalues, they're independent on your z position, so you can just evaluate them, and they don't diverge when you take the limit z to 1, and you get that eigenvalue 1 is -3, and eigenvalue 2 is, if you put lambda to 4, like in the picture, it's a negative number. Now, the last eigenvalue is the problematic one. And what we find is that, well, you can sort of write something down. It's not 100% perfect, but it depends on the sign of the parameter gamma. And effectively, what is happening is you get that the third eigenvalue approaches -infinity. Now, the question to ask here is, does it make sense to consider a point which is singular, which has 3 negative eigenvalues, or, well, 2 negative ones and the third negative one in a corresponding limit, to call this a stable point? And we sort of are of the opinion that that's probably the correct thing to do. But the open question is, can one make this mathematically rigorous? And we don't quite know yet, but we have we have a way to deal with it. So this is the interesting open-ended bit where one can probably do some new mathematics to study dynamical systems that contain singular points. And basically this type of calculation confirms the numerical result that this point behaves like an attractor. And I'll finish almost on time by thanking you first of all. If you're interested in this kind of stuff, we've written a very long review. It's the second one. And you can't read it over a cup of coffee because the archive version is like 180 pages long. But if you like dynamical systems and you're interested by cosmological dynamical systems, this thing is full of stuff that people have done. And this is now 7 years ago. So one can probably add another 100 pages to it, but we will not do this. So thank you very much.
There is 2 parts. There is the first part about the math. In the math, it looks like in the way that you are taking that in the direction of the physics. You look at from point of view of the physics, because there is a lot of terminology that I am seeing over there. For example, when you talk about fixed point, or you talk, for example, when you talk about the eigenvalue and so, you know, this lot of math need to be a little bit more focused and think about it. Because, for example, here when you talk about the eigenvalue is a negative, but eigenvalue is a complex. That means you are talking about the real part of the eigenvalue need to be negative, and correct. All of this story answer.
Correct.
This is need to be really just look and check in some way. The same thing when you talk about the fixed point, it's just an equilibrium, because you are talking about the right-hand side. All of that stuff is just the theory of the dynamical system, which is very, very developed in math. And so I'm not talking about this part, but I am really For example, when you talk about the cosmology models, it looks like it's very simple, yeah? You are presenting just simple differential equation, which you can see sometimes, of course, use a method of dimensionless and so, which really question mark and so in this direction, why we are really trying to kick out all of this information that we have inside of the parameter, so it's useful and so. But the question that I have, I'm not talking about the math or art. Do you believe really the theory we are talking now, more of the people they are killing us about the Big Bang and so, it can be really presented as a simple equation?
You mean that the Big Bang has these
yeah,
simple
from
equations?
The Big Bang until today, we're taking all of these years, you know, with the thousands and thousands of years, is presented as a simple equation, which is just the differential equation 2D or 3D.
I love this question because you're actually correct, right? From a philosophical point of view, how can it be so simple? Because what I've shown you, you know, you can do this after 1 year at university. I could give you the equation that you can say, okay, this is what the universe does. How can it be? I think that the issue is what makes it so simple is that on very, very large scales, it looks homogeneous and isotropic, and that reduces the geometric picture to something that is extremely simple. But remember, one has to be quite careful. You have to say that over very, very large scales, these equations are approximately correct.
Just think about it. You have several years. It could be, you can think about another thing. Take state function, you know, and each time we have another different way how we see that model. It will be completely different. In this case, and I am just, because this is the point, thinking about today and projecting, think it was happened million years and providing this is validating of that model, it's a little bit question mark, to be honest. The point is the following: go into the validation of something, taking a lot of hypotheses, a lot of collecting data, thinking all right, and then after that we can say yes, we can go for this kind of theory is all right. But just projecting things of small things and you say, oh, this is what was happened. This is it. I love it because now you answer to my question that I said no for a long time ago. Why we are thinking too simple in that way? I believe really, if you think you should go for the Einstein model, you know, it's complicated, it's normal, but it's close to some way to the reality. What I think is more real. Thank you.
Thank you.
Thank you.
Thank you very much, Prof. Boehmer. Could you please go to the slide where you have shown the motivated example for cosmology?
The first one?
No, the system, have a system.
With the 3 equations?
Yeah, for two equations, I think. U and V.
Oh, U and V, yes.
Yes, here, okay. So I have here 2 questions. One is a general question, the other one is maybe a little bit technical. For the general question, for people or researchers in cosmology, when they have a model or a system, for example, like that, do they care about the space of functions where the system is solvable? So do they care about the space of solutions?
You mean in terms of how regular the solutions are?
Yes.
No,
they choose any functional space, or what space of function they
yeah, I think I understand your question. My more cosmology colleagues would be looking at you like saying, what is he talking about? No, I totally understand your question. Generally, this question is not asked by people who do this kind of stuff. They basically assume the function is sufficiently regular for all practical purposes.
Okay. For the technical question, for the condition you have here, u square plus v square is between 1 and 0. Do this condition means some physical thing?
Yeah, so to get to this model, it is a concrete model that gets reformulated in this dynamical systems language. The reason those bounds appear, is that your question? Why is it a semicircle? A semicircle, you can almost read it like a type of energy conversation. You want the energy to be less than 100%. So this is usually where these bounds come from. So they are physically motivated. And what you have for this model, for instance, that the trajectories cannot cross the x equals 0 line, and they cannot cross the semicircle. So the system sort of splits into the inside of the semicircle and the outside, and only the inside is physically meaningful.
So this is constraint. So we cannot ignore this condition.
Yeah, so this it gets derived. And you can check that if you differentiate the condition, you get 2u dot and 2y dot. And if you substitute the equations back into this, you see that they're conserved.
Okay, thank you so much.
So, thank you. Right.
Any other questions, please?
Your examples, the example you took are were in Rn, I mean in space of zero curvature. What about I mean the same problems in general Riemannian or Lorentzian manifolds?
Yeah. Do you mean the KCC stability?
Yeah.
So
yeah, the system you took were in R2, R3, in Rn, I mean, where the curvature is 0. I mean, it will be very interesting if you take some examples in any other space-times or Riemannian manifolds where I mean the curvature, Ricci curvature, scale curvature will be involved. You see?
Yes.
Yeah.
Yeah. Shall we discuss this together afterwards? That becomes quite technical, I think.
Okay.
Yeah.
And I have another question about the Euler-Lagrange equation and the geodesic equation. What you said that Euler-Lagrange equation does not cannot be.
Yeah, so if I give you an arbitrary second order Euler-Lagrange equations, what I'm saying is you cannot always write it as a geodesic equation.
Yeah, but the converse is true.
The converse is obviously true. Yes, absolutely. So you can derive the geodesic equation out of Euler-Lagrange equations. Yes, you're absolutely right. But yeah, it's the other way. Thank you.
Thank you very much for the very interesting talk. Actually, I have a simple question about the Lotka-Volterra system. Now, usually in biology, when you have a Lotka-Volterra, then the existence of one species has negative impact on the other species, right?
Correct.
But in your case, the existence of one, I don't know, one quantity has a positive impact on the second quantity. And in the long run, you are interested now in the, I can say, the extinction of both quantities.
Yeah, so you're absolutely correct. So I can give you a mass bio interpretation of this diagram using the Lotka-Volterra language. So you're absolutely correct. So imagine you have three species. One is called R, one is called M, and one is called lambda. Basically, this is the type of model where the species lambda dominates at late times over all other species, and the other two will actually be extinct. So you simply do not get, so in many or in many predator-prey models, you get the typical fluctuation where the two species fluctuate. So in this kind of model, the species, in your language, lambda, dominates all species and the other ones go extinct. But this is the beauty of writing it like this. You see, you can use the other language and the other techniques to sort of think about this. So there's no equilibrium between species. One dominates all the others.
Okay, thank you.
Okay, thank you. Any other other question, please? Okay, thank you, Professor Boehmer.
أهلا وسهلا بكم مرة أخرى. نبدأ الجلسة الثالثة والأخيرة لهذا اليوم مع البروفيسور دانيال ليسنيك والأستاذ الدكتور بندر المحسن.
Greetings. We are pleased to begin our session, chaired by Professor Bender al-Mahsen and featuring Professor Daniel Lesnic, University of Leeds, United Kingdom.
Good afternoon. Welcome back to third session. Our keynote speaker is Daniel Lesnic, Professor Daniel Lesnic. He is a distinguished academic from Leeds University in the United Kingdom. He is a professor of applied mathematics in the School of Math with a strong research on inverse problems and partial differential equation, heat, conduction, numerical analysis. Professor Lesnic has published over 400 papers in high-impact journals. He has supervised more than 25 PhD students. His contributions has significantly advanced the field of mathematical modeling and computational method. He is going to give a talk titled Inverse Modeling of Biological Tissues. Please.
All right, so good afternoon and welcome back. So first I would like to express my gratitude and sincere thanks to Bandar and also Mohammed for organizing this prestigious conference and for inviting me to deliver a talk. So I could say I'm really delighted to be here at King Saud University and Riyadh in general. I'm overdue to visit. You already had missed 2 opportunities in the past, but now it's a great opportunity to meet all of you and try to share some of the contacts we have. So I'm based in Applied Mathematics Department at the University of Leeds in the United Kingdom, which is north of England, I should say. Is probably near to Manchester, about 1 hour drive than it is to London. And we have developed over the 3-4 decades a subject which is called inverse problems. And for some of you, they might be new to this subject. They are the opposite of a direct problem. So a direct problem would be one in which you put a question and you want to find the answer. In an inverse problem, you know the answer, and you want to determine what is the question that gives rise to that answer. Now, in that framework, it fits the process of mathematical modeling in general. When we are taking a phenomenon from nature, and we saw the talk in the morning, you can think about cosmos or universe, then how can we write a simple mathematical model which is able somehow to try to visualize or model the best features of the very complex system. But so it did Einstein. Einstein's general theory, the equations written there, we teach them at the 3rd year undergraduate. They are not extremely complicated and they govern so many good things. And even going back to Newton's second law, that's a very simple law to write down, yet it models so many physical problems in nature. Of course, going in history, you can think of Maxwell equations in electromagnetism, which are non-trivial PDEs to solve and so on. In this application, I'm talking about trying to model something related to biological tissues. In general, I refer to modeling the tissue beneath the skin of the human body, but you can think also on tissues related to other organs such as the thigh or even the eye here. So these are the collaborators. I will say more about the connection with Saudi Arabia at the end, hopefully. So that's a picture which shows you the complex architecture of the blood flow inside the human tissue. And here there is a division going from capillaries, which are very small tubes up to 15 microns in diameters, then move on to secondary vessels up to 100 micrometers, primary arteries and vein, and the main supply, which can become visible of about 1 millimeter in diameter. And through all this complicated system, there is a surrounding tissue, which is mainly based on a different type of material than the blood that flows through these complex tubes, let's say that way. There we okay. Right, so what is the process that we want to describe here is something related to the field of thermal biology or biomedical engineering, if you want to see what is the real application of mathematics to these subjects. And before we go and jump into the partial differential equations that they govern such phenomena, let us say one or two things that they come from the physical mathematical modeling. Basically, we have a tissue like your forearm, and you want to go and do a tomography scanning, for example, of the arm. And there are various ways to do that in the medical world, such as you can do X-rays, you can do MRI, you can visualize kidneys and other organs. All these are quite expensive. Another way might be just be based on so-called hypertherapy, where you heat the tissue to about 42 to 45 degrees Celsius, and then you measure the resulting temperature on the skin, or if you use some biopsy, you can measure the temperature inside the material as well. But what is different in the process of heat conduction is that when you heat the human tissue, it's not the same as you heat a metal. And mathematically speaking, because the tissue is soft and it has various properties through which the heat is supposed to diffuse. Yeah, the heat doesn't propagate instantaneously, and it has a so-called time lag, which is non-negligible. It's about 15 to 30 seconds, and we need to take that into account into the process of heat waves as being modeled as thermal waves, and this what it changes our governing mathematical model from a parabolic PDE to a hyperbolic PDE, in which this time lag tau will appear as a small parameter. Well, it could be small, but it could be not necessarily as small as we can do asymptotics about that. So this type of thermal therapy has been applied before in various applications. And this is just another nice picture taken from a paper where it visualizes the skin on the forearm is made of 3 layers. And one you can see, it's at the surface of your skin, is called epidermis. That's about 0.6 I think millimeters. And then you have the dermis beneath, which contains various glands. And beneath that, it's the hypodermis of subcutaneous, where the adipose fat tissue it's deposited. And if everything goes well, you know, this triple layer system, it's well maintained, and you can delimit, you can solve a problem if you want in a triple composite, if you really want. However, if something goes wrong, then an anomaly may be developing somewhere in between dermis and epidermis, for example, protruding outside the skin, maybe growing inside, and that's called skin cancer sometimes. So that's why it's so important to study how the properties of such a tissue they are. And if we are doing thermal waves or thermal heat conduction, then we would be interested to determine the thermal conductivity or the heat capacity of a tissue, as well as something else which is called the rate of blood flow. Going back now to the mathematics, without much derivation that's available, we can write down the governing second order partial differential equation satisfied by the temperature, which is denoted by T. And there is a perturbation of the first order time derivative, which moves from the parabolic PDE to a hyperbolic one, where you contain the second order time derivative of the temperature in the first term in the left-hand side. You can see the parameter tau, the time lag that it appears there. And there are certain other physical quantities that are present into this PDE, which are listed here, like the heat capacity of the tissue and the blood, CT and CB, the blood perfusion rate, WB, and there are also some heat sources due to metabolism and external heat. And the metabolism is one of the basic functions that if it works well, we are fine, but once metabolism doesn't work well, then some anomaly is likely to develop. And we are to solve this problem in a time-dependent space domain, where D is the space of the T occupied by the tissue, and the time interval is from 0 to some TF. This is a dimensional system where all the quantities involved are with standard units. So as an applied mathematician, the first thing we would do is to non-dimensionalize the system appropriately and work with numbers rather than units. We'll try to do that. Okay, so how that model has become, it's just a modification, first order Taylor series expansion of the classical Fourier series, the classical Fourier law, which expresses that the temperature gradient is proportional with the heat flux. But if you are to take into account for the time lag tau, then that expansion holds, involving the first time derivative of the heat flux. And as you plug this one into the continuity equation, then you recast this as that hyperbolic PDE before. Okay, if you have multiple layers, then you can write this model piecewisely. And let us assume that the tissue, which you saw it in the past, there was a triple layer tissue. It could be an L layer tissue or J layer tissue. And depending on the organ that you want to image, you can have many different layers. For example, for the skin, you have 3 layers, so J is 3. But if you have a tide, there are 4 layers, and in the eye, there are even 7 layers of material. And you have to solve somehow piecewisely the previous model. Of course, we need to supply boundary and initial conditions. And the first ones are just common interface conditions related to continuity of the temperature and the heat flux. You can have imperfect contact through thermal resistance, but we don't take that into account. All of those, they are different problems. And provided that all these quantities are supplied. We have also an initial condition at time t equals 0, and also the velocity is 0. And the other thing was the boundary conditions now at the skin, because that is surrounded by the ambient air. The temperature in the air and the temperature just beneath the skin, they are not the same as you have convection when you look at the temperature at the window from outside and inside. So that recast as a Robin boundary condition convection, which is given here in the first relation involving a heat transfer coefficient H. So that expresses the proportionality between the normal derivative and the function itself. And down deep inside the tissue, we assume an insulation or adiabatic boundary condition for simplicity. And this is just some non-dimensionalization that we can perform. I'll skip some details. They are all these constants, they appear. They have no more physical meaning, but they have mathematical meaning in the fact that they are constants to be identified and they do not have units. And they come into the model without changing its hyperbolic feature. Now, in the previous model, all the quantities and the geometry and the parameters are well specified and taken from the literature. In case of, for example, we want to do a phantom experiment, then determining the temperature T satisfying that initial boundary value problem for the hyperbolic equation is straightforward and well posed based on classical books on PDEs. However, in case that some of the properties are unknown, in this case, we talk about the thermal conductivity and the heat capacity, then there will be, let's say, 3J constants to determine, and you need to supply this missing information by measurements taken elsewhere. And in this case, we assume that we measure the temperature T at some positions inside the skin. It can be non-intrusive if you look at the boundary only, but it could be also intrusive if you take surgery or if you use biopsy in your temperature measurement. Now, another drawback from the fact that this measurement procedure might not be straightforward and it might not be accessible in certain cases. For example, it won't be easy to do that on the head, for example, is the fact that these measurements are noisy, so they are subjected to errors. And because the inverse problem that we solved turns out that it is ill-posed, that means the solution either does not exist, is not unique, or is not stable. There is a price to pay for that, and therefore this small noise into the measurements will amplify drastically into our output unknowns in this case. So we can model that by statistically by perturbing with Gaussian noise. It doesn't matter the type of noise. We don't make any statistical assumptions other than numerical simulation. Right, so these are just some results containing the measurement of the temperature only at the skin surface and at the deep downside end of the tissue. So we have quite a lot of them. They are taken at two boundaries. In this case, it's a one-dimensional slab of material, so the boundaries are just the discrete points 0 and 1, but we do the measurement in time. So we had initially 9 constants to determine, so we may need at least 9 measurements to perform, and because we take them in time, this NIVN can be taken large, and then we have an over-determined system of equations. It is nonlinear, so we can use MATLAB toolboxes such as LSQ nonlinear, which I think now in especially in this mathematical community is well used, especially by PhD students. Right, this is just some input from the physics to test the numerical method. Right, so this figure shows the convergence of the objective functional, which is just the least squares minimization. It is non-convex because the problem is non-linear, so it depends on a good initial guess. But here for what we have chosen, the results are shown with 0% noise and with 0.5% noise. And the convergence with the number of iterations is rapidly achieved. And it produces some results, which if you look only at the relative error, they are small, under 0.5 of all the 9 quantities. And for 0.5% noise, they do increase as you expect, but they are within a physical, region of interest. Now we move on to a related but different inverse problem. Before, the analysis consisted of identifying the properties of a piecewise constant material. So you have a discrete number of unknowns. Now what happens if your unknowns are no more discrete, but they become unknown functions? And this is the case of an inverse coefficient identification problem, where I want to find, in this case, the coefficient of blood perfusion represented by the coefficient WB into the governing hyperbolic PD. So in the inverse problem, we want to find, apart from the dependent variable, which is the temperature depending on space and time, we also want to determine this coefficient WB of X, which is a space-dependent coefficient related to the blood perfusion. Of course, the piecewise constant case is just a space-varying discontinuous example. So this is more general and more difficult. We supply initial and boundary condition of convection type, Robin type, and to determine the missing W of X, we need to measure something else, right? And common sense would tell us to measure something depending on X as well. If you want to write in terms of functional analysis, the forward operator matching K in some nice space or bullet space into the space of your measured data, and that space of measured data, as it depends on X, it could be either the temperature specification at the final time, or you can have the last one, which is an integral non-local measurement. That means you take all these measurements and average in time. But the second and the third are no more, okay, they are different. The second one, it's a measurement at the boundary of the temperature, so that changes our problem's character drastically. And the third one, it seems to contain too much information. You assume that temperature is available in a subset of your domain. So all these, let's say, 4 inverse problems are non-trivial, and they can lead with 4 different research, yet we solve the same problem or the same application, not the same problem, the same application related to thermal waves in biological tissues, for example. So you can see whilst the direct problem, it's only one, and in general, there are not many ways you can formulate inverse problems. You can formulate them in many ways. And you may even ask a very important question: which of these measurements is better than the other, in order to save time and also give to the experimentalists what to measure. So that's only what mathematical or mathematicians can do. Engineers won't be able to decide. They will measure whatever they think. So again, on dimensionalization. And this becomes a one-dimensional model, which is less complicated than the previous one. Yet you can see the governing equation, again, hyperbolic wave type equation with lower order coefficients. and W of X is the unknown. So it appears as a space-dependent coefficient in front of the time derivative, but it's also in the right-hand side, Wx times U. So it appears in both ways, but there are certain techniques that one can apply to solve this inverse coefficient identification problem. Now the extra measurement is the last one written there, is the measurement of the temperature at the upper base at the final time TF. And we have done some numerics for this. Okay, this is useful because especially those of you working with partial differential equation, we seldom look at one-dimensional models because they are too simple. And we like the problem being formulated in higher dimensions, and also it's more physical in higher dimension. Now, what you have is that the second order space derivative is replaced by the Laplacian. So now you are more familiar with this type of model, which you have a hyperbolic PDE with space-dependent coefficient, a free term F. The initial conditions at time t equals 0 in U and du by dt, they are classical. A Robin condition on the boundary, and that's a little bit different because if you look in literature, in general, we solve the Dirichlet-Neumann problem for the wave equation. But there are not so many works on the Robin boundary condition for the wave equation. You can look in the books by Lyons, but the achievements are rather recent in the group of Lazienska and Tataru and so on. And that's the last measurement which is supplied. And okay, we have performed some numerical computations for this problem, for which we are not sure whether the solution is unique, by the way. But this is just the same type of MATLAB LSQ nonlinear minimization. We employ a Tikhonov regularization, which is important to deal with the noise, to recover, to restore the stability. In the left-hand side, you have, in the case of no noise and no regularization, the objective function behavior after 7 iterations. It does decreases very drastically. And in the right-hand side, there is the exact solution, the initial guess, which is a straight line, and the numerical solution, which is the curve. It's a parabola there, and it matches pretty good. Here, when we put noise, 0.1% noise is very small. In the left-hand side, it says that if you do the inversion with no regularization, the solution starts to become unstable. And you can see it's highly oscillatory, and it doesn't predict the straight line. In the right-hand side, we have applied some little regularization to the minimization, and we alleviate this highly unbounded oscillation. It's still not perfect, so we can do more work, such as employing higher order regularizations, like first order or second order. That will do better. Okay, now the last problem that we looked, it was to change the type of measurement, because measuring the temperature at the final time means that at a given instant you have to do that at many points inside the material, so that might not be convenient. And what happens if instead we measure the temperature on the boundary, on the lateral boundary of the skin tissue? So that's represented by the last equation here, where P stands for the temperature measurement on the lateral boundary. So this is a totally different problem. It has its own ill-posedness, and here we managed to establish a theorem which gives us the conditional stability of the problem. There are certain spaces that we need to assume the solution and the data is related to. They are rather technical, but the strong condition is that the initial temperature should be should never vanish. Actually, it should be always strictly positive. And then we can establish the stability estimate, which gives us the difference between two coefficients in L2 of D being bounded from above by the difference into the time-dependent derivatives of the measured data, which in itself it's an ill-posed process because P is measured noisy and you can't differentiate noisy functions. But if you would be able to say that there is no noise in the data, then the right-hand side is a stability estimate, but it's a very poor one because, again, doing that numerically is likely to produce highly unbounded estimates in the right-hand side. So this just highlights the difficulty of the inverse problem. And yeah, to prove this theorem also, it's very complicated based on Carleman estimates and so on, but we managed to do that. Okay, numerically it's easier. We minimize the gap, least squares function. Again, you need a good initial guess, but we employ the conjugate gradient method. We can write down and calculate the gradient pretty analytically based on the solution of the adjoint problem. So you take the Fresher derivative and calculate that. And what happens, you do that iteratively. And because the problem is ill-posed, you need to stop the iterations at a suitable threshold, which is given by the amount of noise with which your original data has been contaminated. So you need to know that epsilon. And once your objective function becomes less than this epsilon, you stop. So we can see that on the graph. This is the example, physical example that we tested. And in the left-hand side, you have the convergence of the objective function with respect to the number of iterations for 0, and that's no noise in the data, and 1 and 3%. Here you can see where for 0, you leave the iterations to run until, say, 20 iterations, but for 1%, you need to truncate after about 5 iterations and so on. And the right-hand side are the numerical recoveries. And you can see that the exact solution is 0.04, the straight line, which is well recovered in the case of no noise. In the case of noise, the results, they start to deviate. But if you look on the y-axis, the errors are pretty small, though. Okay, so 2 more slides. One is with future work. We've been developing this for a number of years, and I will put a slide with the people working, some people working on related inverse problems. So one thing we lack as mathematicians is the experimental data. Quite difficult to talk with engineers to do something, and we can't live so long. So therefore, we may need to do our experiments to learn how to do experiments. And nowadays, mathematicians, we teach them in schools and in university how to do experiments, and that's great. And we will be able to do that on our own. Also, we can assume that the thermal properties, they are temperature dependent as well, and we can move on to solving real medical problems relating to skin tissue detection and allocation. Yeah. I thought I put this last slide just to give you a flavor that this is hard work, and also to acknowledge the fact that there are strong connections between Leeds in particular and my group on inverse problems and Saudi Arabia in general. This is just a list of 5 PhD students. The first one was the great Bandar here, now famous professor here. So nothing was in vain. It was hard work. And he was the first student from Saudi Arabia graduating from Leeds University, applied maths in that particular inverse problems. And since then, Huntul and Al Saimi, now they are back. They are back in Saudi Arabia. Now they bring back all their expertise. I have one PhD student ending this year, and I will take another one next year. So there is plenty of scope to develop the theory of applied mathematics supplemented by numerics and experiment. Thank you.
Thank you, Daniel, for nice presentation. You have 10 minutes for comments, question.
And the other for temperature. Yeah, so let me answer that question if I may. You are right that this model is called the single phase lag, and the one you which suggests is the dual phase lag.
Yes, yes.
And this won't go, but the last slide I put, the student is coming next year. She's going to work on the dual phase lag.
Let us go to the second question. When temperature exists in any system, you should ask about the first law of thermodynamics and the second law of thermodynamics and Clauss-Hamel inequality. This is the basis for obtaining the system of field equations contains temperature in the direct model. What about the inverse model?
Yeah, I mean, with this model, there are improvements that one can make in order, for example, to make sure the second law of thermodynamics is satisfied, I should say. But as far as the inverse model is concerned, it relies on the direct model as such, but it doesn't have any effect other than the difficulties encountered in the inverse model are the same as with the direct model, if that is related to the modeling on its own. But other than that, that can be treated as a wave type problem as well. So it's just inverse problems for hyperbolic equation PDEs. In fact.
Thank you.
Second question there.
Thank you very much. It's a nice presentation. I have a few questions. One, you're using you're trying to find the parameters, right? And instead of using the contrast between the actual normal parameter.
Well, you have mentioned something. So if I understand correctly, there are some parameters to identify, and we do that by taking measurements because those parameters are unknown. We may know something about them as a priori estimates, but we don't know exactly. But we do some experiments in which we measure, we measure the temperature, or we can measure the average of the temperature or something like that. So that's what we do. I mean, there are many ways this can happen, and we can discuss about that. So first, more measurements doesn't mean necessarily more information, because all these measurements are noisy. So you add more noise along with the more measurement that you do. So there is a limit to that. Now you can have your number of unknowns in general has to be less than the number of your data. Yes, yet that doesn't deal with the stability by having more data. Stability is dealt with by using this process of regularization, where the functional that you minimize is added a Lagrange multiplier penalty to it, and that's how you restore stability. So I think it's not done by more measurement or less measurement. It's done by the algorithm itself. The problem is still ill-posed, as we saw from the result there, for example.
شكرا للأستاذ الدكتور بندر المحسن والبروفيسور دانيال ليسنيك، وشكرا لكم جميعا على حضوركم اليوم.
Thank you, Professor Daniel Lesnick and Professor Bender al-Mahsen. Thank you all for joining us today.
حضورنا الكريم، يا من سعيتم في رحلة البحث عن العلم، يا من أبحروا في أبحاثهم واكتشافاتهم وسعوا إلى نور العلم وضيائه، اليوم تكرمون وتشكرون على جهودكم، واليوم تعلمون وتشاركون معرفتكم. اعملوا وتشاركوا معرفتكم، فأنتم في فرصة يسعى لها الكثير، ومدعوون بمعرفة ترضي شغفكم بإذن الله.
Today, we honor and appreciate your dedication. Today, you inspire and impart your wisdom. Engage deeply, connect with your peers, and together, let's shape the future of mathematics. Share your expertise, for you stand in a position many aspire to, one where knowledge fuels your passion and drives progress. Thank you all for joining us today. And now let's move on to our final event, the poster presentations, which will take place outside. We look forward to seeing you there.
والآن دعونا ننتقل إلى آخر فعالية لدينا لهذا اليوم، وهي عرض الملصقات العلمية والتي ستقام في المعرض الخارجي، ونتطلع لرؤيتكم هناك. والسلام عليكم ورحمة الله وبركاته.